In this video, we're going to take a look at a trigonometric identity known as the Pythagorean identity. But what is a trigonometric identity? Well, if we took a look at the Wikipedia page entitled List of Trigonometric Identities, the first sentence tells us that in mathematics, trigonometric identities are equalities that involve trigonometric functions and are true for every single value of the occurring variables. Now what this means in basic terms is that they're an equation that involves one or more trigonometric functions and that are true for every possible value of the variables in that equation. Now without realizing it, we've actually seen some trigonometric identities already. For example, we saw that the sine of an angle theta is equal to the ratio between the opposite edge and the hypotenuse in a right-angled triangle. This is a trigonometric identity. For every possible value of theta, along with the possible lengths of the opposite and hypotenuse edges in a right-angled triangle, this equation holds true. And because this equation involves a trigonometric function, it is therefore a trigonometric identity. Now, trigonometric identities are incredibly useful for solving problems with trigonometry, because by equating some trigonometric function to some other combination of variables or trigonometric functions, it can allow us to apply the equation to find unknown information in a problem. We've seen that. We've used these trigonometric ratios to find both edges and angles in a right-angled triangle, but it can also allow us to use the equation to replace unknown parts of some other equation. Now this is just going to be a completely arbitrary example. I'm just making this up and it has no real bearing to anything in terms of practical application. But let's say that we had an example equation that was x is equal to the cosine of theta plus the sine of theta. And for whatever reason we didn't know the angle theta and we didn't know the value of sine of theta, but we did know, let's say, this value, the cosine of theta. We could take this, and if we knew the opposite and the hypotenuse, we could replace the unknown part of the equation with something that we do know. So we could say x is equal to the cosine of theta plus the opposite over hypotenuse. Again, this is just a completely arbitrary demonstration with no practical purpose whatsoever. But it does show that it's very useful when we know certain variables and not other variables, because we can find identities that express the unknown variables in terms of known variables, and then we can use that to start solving the problem. So again, that was an arbitrary demonstration. It has no real practical purpose, but it's just to show that if we do have this long list of various trigonometric identities and we know some of the values but not others, we should be able to start combining these identities together to give us the answers that we're looking for. And there's a really basic identity that we're going to start out looking at in this video. That's the Pythagorean identity. And then over the next few videos, we're going to take a look at some of the other most common trigonometric identities that I believe are some of the most useful identities to be aware of. Of course, there are many more identities than I will be covering in this DVD. The Wikipedia page that I just referenced has an extensive list of various identities, and once you have a grip of the basics, once you understand the basics, it really is a fantastic reference for seeing all of the various trigonometric identities. So the Pythagorean identity that we're going to be looking at in this video, I believe it's one of the most basic of the trigonometric identities, and that's because it's derived quite simply by looking at the unit circle, which is how we actually defined sine and cosine, if you remember back to the earlier video where we defined both of those functions. So allow me to draw a unit circle, which, kind of cheating, I already have part of that drawing done for us already. And if it's a unit circle, we know of course that the radius of that circle is going to have a length of 1 unit. We know there's a point on the circle which has the coordinates x, y, and we know that we can say there's an angle, anti-clockwise angle from the x-axis to our radial line that has the angle theta. And we saw when we defined sine and cosine, we said that y is equal to the sine of that angle theta, and x is equal to the cosine of that angle theta. That is, in fact, how we defined sine and cosine. Now, if we took that point on the circle and we construct a right-angled triangle from it, much like we did when we were defining tangent, and as you're actually going to see, this is almost identical to the approach we took back in volume 1 to derive the equation for a circle. So I'm going to create a right-angled triangle here from that point down to the x-axis, such that the radial line is our hypotenuse, and then we have two other edges, one running parallel to x, one running parallel to y. Now we know the edge that runs parallel to x goes from 0 in x up to our x coordinate in x. That means it has a length of x. Likewise, our edge running parallel in y goes from 0 in y to our y coordinate in y. That means it has a length of y. Now we can apply Pythagoras' theorem to this right-angled triangle, and that tells us that x squared plus y squared is equal to 1 squared. And of course we know that 1 squared, since 1 is just a number, we can evaluate 1 squared, and that gives us the value 1. So we know that x squared plus y squared is equal to 1. But we also know that x is equal to the cosine of theta and y is equal to the sine of theta. So we can place those into our equation, and we can see that the cosine of theta all squared plus the sine of theta all squared is equal to a value of 1. And if you recall back to when I was talking about the inverse trigonometric functions, I mentioned there's a notation that allows us to write the sine or cosine or tangent of an angle then raised to a power simply as the function raised to that power. So this cosine of theta all squared can be written as cosine squared of theta. It's just a notation. The value hasn't changed in any way. It's just a way of saying we work out the value of cosine of theta and then we square it, plus sine squared of theta is equal to 1. And this actually is more commonly written as sine squared theta plus cosine squared theta is equal to 1. This right here, sine squared theta plus cosine squared theta is equal to 1, is our Pythagorean trigonometric identity. Now this identity itself only occasionally comes in handy. If we say know the cosine of an angle, we can find the sine of the angle, or vice versa. It can also be very useful for deriving and proving more complex trigonometric identities, though we won't actually see that in this DVD. But if you get into more advanced trigonometry and you start looking at some of the more complicated identities that are, for example, on that Wikipedia page, you will see that sine squared theta plus cosine squared theta equal to 1 can be used to prove these more complicated identities. So although this identity itself perhaps isn't that useful in and of itself, it's more useful for more advanced trigonometry, it is one of the most basic identities. I did want to cover it in this video, and we can actually use it to find unknown information in certain more theoretical and not entirely practical examples, but we can actually use it. So talking of theoretical and not practical examples, allow me to draw a triangle. So I'm going to draw a triangle, and that vertical edge is a little bit off, but that doesn't matter. Just imagine that this is a nice right-angled triangle. And let's say that the only piece of information we know about this triangle is the hypotenuse has a length of 12 units. Now, if we were to try and find the length of this edge, the base edge, we can't currently do it. We don't know the length of our third edge, which means we can't use Pythagoras to find the length of that unknown edge. And we also don't have either of the two angles here to be able to apply our trigonometric ratios to find the length of the edge. But let's say that someone came along and they told us, hey, I know that this angle, which I'm going to call theta, I'm not going to tell you the actual value of that angle, but I am going to tell you that we know the value of the sine of that angle. So let's just say we know the value of sine theta is some number that's between -1 and 1. We don't know what theta is itself, but we know the sine of it. Well, we all know that we could just use the inverse sine to find the actual angle in the triangle, and then once we've got that angle theta, we can use our trigonometric ratios to find this unknown edge. We know this unknown edge in relationship to theta is the adjacent edge. This is, of course, the hypotenuse, and that means we could use the cosine of theta, which is equal to the adjacent over the hypotenuse. So that means our adjacent edge, our unknown, is equal to the hypotenuse times the cosine of theta. Fair enough, we could take this approach to find that edge, but let's just take a look at an alternative approach where we're going to use our Pythagorean identity. Now again, this is just a theoretical example. It doesn't really have much practical use because, as you see, we could just use our inverse trigonometric functions to find theta, then put theta into this equation and find out the length of the adjacent edge. But I do want to show how we can more importantly work with this Pythagorean identity more than actually show it for a practical example. So let's say that we know our Pythagorean identity. We can use that to write a value of cosine theta in terms of sine theta. We know the value of sine theta. We can rearrange our sine squared theta plus cosine squared theta is equal to 1 to rearrange this so that we get cosine of theta in terms of sine theta and other numbers that we know, and that would then allow us to plug that into this equation and again work out the length of that adjacent edge. Again, this is theoretical, but just bear with me, it's just so you can see working with rearranging this identity. So let's start out and let's get the cos term, the cosine term, on its own. So to do that, I'm going to say the cosine squared of theta is equal to, I'm going to subtract sine squared of theta from both sides. That gets the cosine squared of theta on its own, but we don't need the cosine squared of theta, we just need the cosine of theta. So I'm going to take the square root of both sides. That leaves us that cos theta is equal to, we're taking a square root, so it could be plus or minus. Again, we discussed that back in volume 1. And that's plus or minus 1 minus sine squared of theta. So notice there are actually two possible values for the cosine of theta when we know the sine of theta. And this actually makes sense. If we were to look at the unit circle, we know that a value of sine theta gives us a y-coordinate. Well, notice for any y-coordinate, I could pick on this guy right here, there are 2 points on the circle that share that y-coordinate. Each of them have a different x-coordinate. There are 2 possible values of cosine of theta at x-coordinate when we know one value of sine theta, our y-coordinate. And in a similar way, there's actually 2 possible values of sine theta when we know cosine theta. If we knew that cosine theta was equal to this negative value of x, there are 2 y-coordinates that satisfy this. One is positive and one is negative. So you're going to see if we're using our trigonometric identity, our Pythagorean identity, to rearrange this either in terms of sine or in terms of cos, you're going to see that we get a plus or minus square root because there are 2 possible values that we could get that satisfy that equation. But we now have this value of cosine of theta. Because we have this value of cosine of theta, we can plug it back into our equation, and that tells us that the adjacent is equal to the hypotenuse times either the plus or minus root of 1 minus sine squared theta, which can be more cleanly written as the adjacent is equal to plus or minus the square root of 1 minus sine squared theta times our hypotenuse, because if we had a minus here, we'd simply take the hypotenuse times the minus. It would give us a negative value. If we took the plus, we get the hypotenuse times the plus, it would give us a positive value. So why not calculate this value once and then take the positive or the negative of it? Interestingly, we're dealing here with the length of an edge. We've already discussed back in volume 1 again, when we're dealing with plus or minus roots, we have discussed that if we're dealing with a length of an edge, we only need the positive value because we don't have a negative length. We only ever have a positive length. So we can say that our adjacent is simply equal to the square root of 1 minus sine squared theta multiplied by our hypotenuse. Therefore, if we got told that we knew the value of sine theta, and we knew the value of our hypotenuse, we take the value of sine theta, square it, we take 1 minus that value, we then find the positive square root of 1 minus sine squared theta, and then multiply it by our hypotenuse, and that would give us the length of the adjacent edge. Now you notice again, this is more of a demonstration of rearranging the Pythagorean identity, and more importantly, I wanted to demonstrate the fact that for a given value of sine theta, there are two different values of cosine theta that basically relate to that value of sine theta, and likewise for a given value of cosine theta, there are two values of sine theta that relate to it. And that's the most important part of what I wanted to demonstrate here, just so that if you are rearranging a Pythagorean identity or any other identity that deals in terms of squares of the trigonometric functions, you do of course remember that when you take a square root, it can be plus or minus the square root, and so you don't ever want to overlook that, because then you'll be removing possible answers from the solution. So we've seen, again, this is just more of a demonstration, but hopefully it's kind of apparent this can be quite useful, even though in that case we had other methods of finding a solution. Let's say that there weren't other methods, then perhaps rearranging the Pythagorean identity or any other identities can be very, very useful to us. Now, because the identity on its own is so really very simple, there's not that much to test here. So I'm just going to set one question, and this question is just to test your understanding of the identity, rearranging the identity, and the various sort of theories that I have covered in this video. So I'm just going to set one question. I'm going to bring up a new whiteboard for that. Fantastic. Scroll right back up so we have room to do our working. And this question tells us that if we know the cosine of an angle is equal to 0.6, then I'd like you, using the Pythagorean identity, to find the possible values of the sine of the same angle. So again, using the Pythagorean identity that we've seen in this video, it's the focus of this video, can you tell me the possible values of sine theta if the cosine of theta is 0.6? So go ahead and pause the video, give this an attempt, and when you come back I am going to work through the answer on the whiteboard. Okay, welcome back everyone. So we're using our Pythagorean identity here. We've seen already that that of course is sine squared theta plus cosine squared theta is equal to 1. That is the focus of this video. And we're rearranging this to find the value of sine theta in terms of cosine theta. So this simply means we can subtract cosine squared theta from both sides, and then take the square root. So sine theta is equal to the square root, not forgetting of course it's plus or minus the square root of 1 minus the cosine squared of theta. So if the cosine of theta is 0.6, then the square of that is going to be 0.36. So sine theta is equal to plus or minus the square root of 1 minus, and I guess we could actually write this extra step in, so 1 minus 0.6 squared is equal to plus or minus the square root of 1 minus, and then again 0.6 squared is 0.36, so 1 minus 0.36 is equal to the plus or minus the square root. 1 minus 0.36 is 0.64. Now the square root of 0.64 is 0.8, so it's going to be equal to plus or minus 0.8. That means our sine theta is either equal to a positive 0.8 or it's equal to a negative 0.8. They are the two possible values for sine theta. Again, it's quite simple. It just wanted you to rearrange a trigonometric identity, and the only real catch here is remembering that of course there's a positive and a negative value for the square root of 1 minus cosine squared of theta. As long as you catch that, you're going to get the two values that we were looking for. So again, to recap, we saw how we could use the unit circle. If I bring all of this back, we saw how we can use the unit circle to relate our sine and our cosine to a value of 1 using Pythagoras' theorem. And once we've derived that relationship, it gave us the Pythagorean identity of sine squared theta plus cosine squared theta is equal to 1. So whilst the examples of how we can use this identity in this video are very basic, very theoretical, not at all practical, it is an identity worth remembering, as occasionally it can be quite useful, and certainly when you're trying to prove and derive more complicated trigonometric identities, it is incredibly useful. So I did want to cover it because it comes up so often in the sort of larger topic of trigonometry that couldn't really have a video on the fundamentals of trigonometry without mentioning this particular identity. So it's a very simple identity. You now know where it comes from. Hopefully you understand how to work with it a little bit, and that is going to conclude this video. Thanks a lot for watching, everyone.